Hello everyone, good evening. So we are in the 10th session of the ray optics part. So probably we'll have, I think, 3 more sessions on this. One session on the lenses. So this session also we are going to discuss about the lenses, and we'll have one more session on lens. Then we'll have 2 sessions on the optical instruments. So that will summarize the ray optics part. So probably from the next week onwards, right, we'll start the wave optics also. But you guys need to make sure that you are solving relevant problems so that you will get the practice, and check with me if you have any issues in terms of approaching numericals. Okay, because this ray optics and wave optics, right, it's a area where we should definitely be able to score well. So even from JEE mains or advanced, even for the NEET also, right, we'll have good weightage for this topic. Okay, so we'll get into the discussion. Actually, what we were doing in session 9 is we have talked about the refraction at a spherical boundary. So we talked about the refraction at a spherical surface. So in this also we have seen, like we may have the object which is kept on the concave side, or we may have the object kept on the convex side. Okay, like this we have seen the scenarios. But to find out the image position, right, we have the equation that will relate the position of the image and position of the object with respect to the radius of curvature for this spherical surface and the refractive indices of both the medium. So here we'll have medium 1 and medium 2. So the formula, right, I hope you guys remember the formula. What is the formula? So we'll consider the medium 1 refractive index is mu1, medium 2 refractive index is mu2. So mu2 by V minus mu1 by U is equal to what? Mu2 minus mu1 by R. So this is what is the formula we have to understand the image for a refraction happening at a spherical surface, correct? So we'll try to study the lenses using the concept of refraction at a spherical boundary. Okay, but before we go to the lens, right, we need to understand what actually is this lens. See, lens, right, you consider the lens to be like a transparent medium which will allow the light to pass through it, and that is bounded by 2 refracting surfaces. So for a lens, right, we will be having 2 refracting surfaces, because obviously when the light rays have to go through that transparent medium, means like you look at this one, right, here you will have refraction, and again this side also you'll have refraction. So there will be 2 refracting surfaces, and in that, right, at least one of them should be having a curved surface, because if both of them are plane, right, already we talked about it, refraction through a rectangular glass slab, that we have considered separately. So we should have at least one of these surfaces to be curved. So here when we talk about the curved, right, in our purview, what we'll consider is the spherical curvature. We can also have the lenses where the curvature need not be spherical. Okay, but that is a little bit beyond our purview. What is there in our purview is when we have the spherical curvature. Okay, like you can see, we are giving them some names. The first lens that you see over here, right, what are we calling it as? We are calling it as the biconvex lens. The first one, right? We'll be calling it as what? The biconvex lens. So why are we calling it as biconvex lens? So if you look at from this side or this side, how does this lens appear to us? It will appear to have a convex. That's why it is called as what? Biconvex. Similarly, look at this one. We are calling it as what? A biconcave. So biconcave, whether we observe it from the first side or the second side, right? You will see the concave surface. Now, when we talk about the general way of looking at a biconvex lens or a biconcave lens, these two lenses, right, is what we will be generally referring to as a convex lens and a concave lens. So when we generally say a convex without putting any other statements, it refers to what? This biconvex. Similarly, when we talk about a concave lens, means we are referring to what? Biconcave lens. Now, how do we differentiate between them for general observation, right? If you look at that biconvex lens, at the center or the middle, it will be thick. Periphery, it will be becoming thin, like you can see. It will be thick at the middle, and periphery, it will be what? Thin. What about the biconcave? At the middle, it will be thin, and when you go to the periphery, it will be thick. Like when we talk about the corrective lens for the eye defect, right? We will be able to understand what kind of an eye defect is the person having by just touching that lens. Like I am wearing spectacles, right? I can just touch the lens in the middle if you touch it, right, and in the periphery if you touch it, depending upon whether it is thick at the middle. Thick at the middle means what? It will be a biconvex. Thin at the middle means it will be what? Biconcave. That way we will be able to understand what is the nature of that lens practically. Then we can also have one surface which is plane, other surface is convex. So we'll call it as what? Look at this. The first side we'll see a plane, second side we'll see convex. So we'll call it as what? Plano-convex. If on one side you have plane, other side you have a concave, we'll call it as what? Plano-concave. Okay. Now look. Okay. So the main type of lenses that we will be trying to analyze in our discussion will be the biconvex lens and biconcave lens. Now in that also, right, whenever we talk about a spherical boundary, we will refer to the radius of curvature. We will refer to the radius of curvature, right? So here, if you have both the radius of curvature same in terms of value, take for example a convex lens, the biconvex lens. We know that for this side, right, where the center of curvature will be over here. So this distance will be what? R1. For the second refracting surface, center of curvature may be somewhere over here. Okay. So this distance will be what? R2. Now if the R1 value is equal to R2, right, means both these spherical surfaces, they are identical. We will call it as equiconvex. What do we call it as? We will call it as equiconvex. So equiconvex will be when both the refracting surfaces radius of curvature values are same. We will call it as what? Equiconvex. If in case of that biconcave, when both sides the radius of curvature values are same, right, we will call it as what? Equiconcave. Okay. So most of the cases when we are talking about this biconvex lens or biconcave lens, we would be having the radius of curvature to be same, but it is not like always it is going to be same. Okay. Sometimes we may have the radius of curvature also to be different. So we should be open for that. Okay. Now we'll see as we get into the discussion, right, what role this radius of curvature will actually play. So obviously when the radius of curvature is changing means what? The refracting phenomena will be having a difference, right? So that is going to result in some kind of an observation that we will make with regard to the overall image formation of the lenses. Okay. So what kind of an effect the radius of curvature will have on the image formation, we will be able to understand as we get into the discussion. But this is broadly how we look at these various combinations of these refracting surfaces. And as I said, the two important ones that we look at are what? The biconvex and the biconcave. And one important point is we should have at least one of the surfaces to be curved. If both the surfaces are flat, right, then we are not going to be calling it as a lens. And here, for most of the discussion, right, we may have, like you see, if you have a lens here, this side you have one medium, other side you have, like, you know, here it is medium 1, here it is medium 2, this is the lens medium. Okay, now most of the cases, the way we are going to use the lens, the assumption is that on either side of the lens we have the same medium, which means if you are keeping a lens in the air, means what? Left side we'll have the air as the medium, right side also we'll have air as the medium. Okay, that is how we are going to study the lens phenomena in most of the cases. It might happen that on one side you may have a different medium, other side also you may have a different medium. That kind of situation also will be possible. Okay, so we'll see, you know, if that happens, what will be the effect of it. But generally, you know, we'll say, for example, we'll say we are keeping the lens in the water, means on left side also we'll have water, right side also we'll have water. If we say we are keeping the lens in the air, means left side also we'll have air, right side also we'll be having the air, like that. Okay, now let us look at the convex lens. Is what? Biconvex lens. Okay, when we have a biconvex lens, we will generally refer to it as a converging lens. Obviously, when we use the word converging, means what? If you pass a parallel beam of rays, then the lens will be converging. That's how the name converging lens has come. Now for this converging lens, which is the convex lens, what are the important points of measurement? Like for every mirror, right, we have, remember, for the spherical mirrors, right, we have what? The pole, then we have the radius of curvature, center of curvature point. The distance from pole to the center of curvature is what? Radius. And we have the focal point. This is of course for the concave mirror. Convex mirror also will have these points, but the positions may be different. Like, you know, we have certain important points of measurement for the mirrors. Same way for the lenses also, right, we'll have some important measurement points. So what are those important measurement points? For a lens, right, the midpoint of the lens. Okay, so here if you look at the line that cuts the lens into two parts, right, this way, we'll call it as the lens axis. Okay, so here the optical center is basically, like, you know, the midpoint or the point of symmetry for the lens. And whenever we are measuring the distances, right, we are going to be measuring the distances from this optical center, all the distances, like the way in case of mirrors, right, all the distances we'll measure from where? Pole. Here we'll measure all the distances from the optical center. So look at this one, we are representing the centers of curvature. So where are we representing center of curvature? We have to look at the surfaces first. So always, right, like the way we follow the convention, we are going to keep our objects on the left side, which means the light rays coming from the object, right, will first undergo refraction at this surface. So we'll call it as the first refracting surface. Then the other side will be the second refracting surface. Look at this, for the first refracting surface, right, you think about the sphere which is made up of that refracting surface, and where the corresponding center will lie, it will be actually lying on the right side. That is where C1 will be. So the radius, right, of this particular spherical surface is basically called as what? The radius of curvature, R1. And here, since we measure this towards the right side, here, no, we are measuring it in the direction of the incident ray. That's the reason why R1 will be taken as what? Positive. Whereas when it comes to the refracting surface 2, right, look at this. When we come to the refracting surface 2, this is the refracting surface 2, right? Think about the sphere of which this is made up of. Where is the center of curvature? It is here. Means this distance, right, we are measuring it to the left side, which means we are measuring in direction opposite to the direction of the incident ray. That is why it will be what? Taken as a negative. So this is a sign convention, like the way we do in the case of mirror, right? Here also similar. From the optical center, any distance you measure to the right side. Right side means it is not like, we are saying right side. What is the actual sign convention? If the distance are measured in the direction of the incident right, then they will be taken as positive. If the distance are measured opposite to the direction of the incident light, then we will take them as what? Negative. Okay, so this is about the converging lens, which is generally what we will refer as the convex. Okay, now the moment we say converging lens, it is not like it is always a biconvex. You can have a plano-convex, right? Plano-convex also can be converging. And after some time we will see that the so-called convex lens also, right, can also be put in a situation where it will be able to show divergence. We'll talk about those cases, special cases later, but yeah, generally when we use the word converging lens, we are talking about what? This biconvex lens. And as I said, the R1, R2 values may not be equal. R1, R2 values may not be equal. If they're equal in terms of value, means we'll call it as what? Equiconvex lens. Okay. Now let us look at the diverging lens. So generally when we use the word diverging lens, we are talking about what? This concave lens. Okay, so what is this concave lens? On both sides, when you observe the surfaces, they will be concave in nature. That's it. So here look at it. This is the refracting surface 1, right? So for this, where is the corresponding sphere center? It is here, left side. So we will measure the R1 to the left side here. That's the reason why it is what? Negative. What about the refracting surface 2? Look at this. The corresponding center will be here. So we will measure the R2 to the right side. Okay. So here also all the distance are going to be measured from the optical center. So this is about the way we look at the measurement of R1, R2 for a concave lens. Now, when we talk about the mirrors, right, we made some assumptions. Can you just recall what are the assumptions we have made in case of the mirrors? We said a mirror will have a small aperture, then the light rays are assumed to be parallel to the principal axis, almost. Means they will be close to the light rays coming, will be very close to the principal axis. Okay, so these are some of the assumptions that we have made in the case of the mirror. Now here in case of lens, right, one of the very important assumption that we will consider, if this assumption is not met, then whatever the lens problems we have to solve, we have to go in the general approach, and whatever the derivations or the results we will have, right, they all are done by assuming that the lens is a thin lens. What do you mean by a thin lens? Thin lens means you look at this thickness T, this should be very, very small or negligible. What happens if this is a small or negligible value? Now if this is small, right, see, for the refracting surface 1, it will form an image. The image distance, right, this is I1, is the image formed by the refraction at the first boundary. We will measure the image distance by what? V1. Now for the second refracting surface, this is going to act like an object, correct? So this is object 1, the original object. Okay, I1, which is the image formed by the refraction at the first boundary, right, that is going to be the object for the refraction at the second boundary. Means this is what is object 2. So when we say we have to measure the object distance for the second refraction, right, we have to measure from here to the location, which is what you are calling as U2. Now if it is a thin lens, right, the value of V1 will be equal to U2, because thin lens, T is what, almost negligible. So V1 will be equal to U2, means the image formed by the first refraction, we are taking it as the object for the second refraction, right? The image distance and object distance values, they would be becoming same when we assume that the lens is a thin. If it is not a thin lens, means then what is going to happen? The V1 value will be different from U2, and that's when I said we have to solve all these problems wherever it is not a thin lens, right? We have to solve them by taking the general approach. But the assumption that we make is what? The thin lens assumption. Okay. Now thin lens and the other assumptions which we have made in case of mirrors, right? Small aperture, that will still be true here. So we will consider the lenses to be having what? Small aperture. So if you look at the lens from the sideways, right, you can see that the lens to be having some kind of an circular boundary. So that the diameter of the circular boundary, right, will be very small in comparison to the radius of curvatures. So the D value will be what? Very small in comparison to our R1 and R2 values. That is what is the small aperture assumption. Okay. So here the thin lens assumption is the most important one. Then of course the assumption we have made in case of the mirror, which is the small aperture, right, that also we'll be using in dealing with the lenses. Now when we look at mirror, right, we talked about the focal point. So remember, what is the definition for the focal point? If you have a concave mirror, so when we pass the parallel beam of rays, they will converge to a point. This point we called as the focal point. What about the convex mirror? When we pass a parallel beam of rays, they appear to diverge from a point on the other side. That point will be called as what? Focal point. This is how we define the focal point. But for lenses, right, here when we say lenses, we are generally talking about what? The convex and concave lenses. For the lenses, we will have two focal points. For each lens, we will be having two focal points. So we will generally refer to them as f1 and f2. How we will refer the focal points as? We will refer to them as f1 and f2. Now the way we will define these f1 and f2 values will be little different. Okay. So let us see how we are going to define this focal point 1. If we have an object, for both these lenses, the same kind of definition. If you have an object which can form an image at infinity, means what? After refraction, after complete refraction from the lens, the light rays should go parallel to the principal axis. So we think about an object, we have to keep the object at a particular place where the image of this, because of the lens, will be formed at infinity. Means after the refraction phenomenon, right, the light ray should be moving parallel to the principal axis. So for a convex lens, if you look at what is that point will be on the left side of the lens. So here the point f1, that is what you are asking. If we look at the light rays coming from the f1, right, after refraction at both the surfaces, the light rays will emerge parallel to the principal axis. And by the way, what is the principal axis? The line that connects the optical center P with the C1 and C2, because for every lens we have these 3 points, right? We have optical center P and then C1 and C2. So the line that connects these points will be what? It is the principal axis. In case of the mirrors also, we have used almost similar kind of a definition, right? What is it? the line that will be connecting the pole and the center of curvature. That is what we call as the principal axis there in case of mirrors. Okay, why I am trying to always recall the mirror concept is because these are interrelated. It is not like they are separate. They are essentially what? Interrelated. Okay, now in case of the convex lens, if you look at this f1, right, the distance of this f1 from the optical center, we'll be measuring it towards the left side here. So hence, f1 will be what? F1 is going to be negative. The value of f1 will be what? Negative for the convex. Now for the concave lens, how we will achieve the refracted rays emerging parallel to the principal axis is, if we have rays which are incident on the lens such that they are pointing towards a point on the right side. Now this point will be called as the focal point 1. So after refraction, right, we will see that the light rays will be emerging parallel. So hence, the focal length in this case will be measured to the right side. So in this case, f1 is what? Positive. So what is the basic idea of the first focal point f1? We have to take an object somewhere so that after refraction, the light rays will emerge parallel to the principal axis. Okay, so in this case of convex lens, the object that you see here, right, it's actually what? This will be a real object. But in the case of the concave, lens, right, what is the object that you see here? The light rays appear to converge to the point, right? What is that kind of an object going to be called as? We will call it as what? Virtual object, right? Remember the definition of virtual object? Which one we will call as a virtual object? If light rays appear to converge to a point, that point will be called as a virtual object. Okay, so this is about the first focal point f1. But while we have discussed so much about it, right, when we talk about the focal point, or when we talk about the focal length of a lens, we will not be referring to these f1 values. We said no, we will talk about two focal points and hence two focal lengths. But when we are generally referring to the focal length of a lens, we will not be using this f1. Instead, we will be using the f2. So we will have to understand what is this f2. So f2 is straightforward, which is like kind of a reverse of what we did. If we pass a parallel beam of rays through the lens, okay, so look at this, the convex lens, we are passing a parallel beam of rays. After the refraction, they will converge to a point. In the case of the convex, they will converge to a point. That's why we are calling it as what? A converging lens. The point here is marked as what? f2. And this distance, right, from the optical center to the f2 is what we call as focal length 2. For the concave lens, when we pass a parallel beam of rays, after refraction they will diverge, but they will appear to diverge from a point. This point will be called as what? f2, focal point 2 for the concave lens. Now here you can see this distance will measure to the left side, right? So for the convex lens, what is f2? Positive. For the concave lens, f2 is what? Negative. As I said, when we are using the focal length value for these lenses, which value we are going to be using? We will be using the focal length 2 and not the focal length 1. So if you try to understand what is the relation between this f1 and f2, right? If we go by the assumptions, what are the assumptions that we are talking about? The lens is a thin lens, and on either side, like the left side and right side, if both the medium are same, when I say both the medium, right, I am not talking about the lens and the outside. I am talking about here we will have outside 1, outside 2, right? They both must be same. If these two conditions are satisfied, then the f1 and f2 values will be numerically same. Sign wise they will be different, because you can see in the case of the convex, right, f2 is what? Positive. But already we have seen f1 will be what? Negative. Sign wise they will be different, but numerically they will be same when we have the lens to be a thin lens and the left side and the right side, right, we have the same medium. Then we will have the principle of reversibility of light, because when light rays are going from one medium to another medium in a particular path, they will be able to exactly come back in the same manner. So that will be applicable when we have the thin lens and when both the sides the medium is same. Okay, so this is about the understanding of the focal points. We'll have two focal points, but we'll be considering only what the f2. Okay, so for the sake of clarity, when we talk about convex lens focal length, right, it will be what, because f2 is what we'll consider, it will be what, positive. For a concave lens it will be what, negative. Okay, now you might want to recall quickly, because we should not confuse between the lens and the mirror concept, but wherever there are some similarities, right, we should be able to try and use them so that we will be able to easily remember. So look at this. What about a convex mirror? Convex mirror, right, focal length is what, positive. For a convex mirror, focal length will be what, positive. For a concave mirror, focal length is what, negative. So you'll see they are, convex mirror positive, convex lens also positive, concave mirror negative, concave lens also is what, negative. So that way you will be able to easily remember the idea that, okay, when we say convex means whether it is a lens or a mirror, focal length is what, positive. When we say concave, whether it is a lens or a mirror, focal length is what, negative. That is how we will be able to easily remember it. Okay, so this is the idea of the focal length for a concave lens and a convex lens. And when we see for any lens, right, forget about the idea of just the convex and concave lens. For any lens, if the lens is converging in terms of nature, right, then when we are passing a parallel beam of rays, this is the method in which we will find the focal length, right. When we pass a parallel beam of rays, what the converging lens will try to do, it will try to converge to a point on the right side. It will try to converge the rays to a point on the right side, right, which means for converging lenses, focal length will be what, positive. So this is another important standard statement that we can remember. For the converging lens, focal length will be coming as what, positive. Similarly, when we pass a parallel beam of rays, diverging lens means what, it will diverge. So we'll see that light rays are diverging from a point on the left side like that. So which means what, for a diverging lens, the focal length will be what, negative. So this is how we'll understand the difference between a converging lens and a diverging lens. Okay. Now we'll come to the important part, which is the image formation. So when we talk about the image formation, right, so we have an object, a lens will have what, two refractions, one at each boundary there will be refraction. Because of that, you will have the final image being formed. So we are not interested in the image happening at the first refraction and image happening at the second refraction like that. We are interested to know just where the final image is going to be formed. That is what is our interest, right? So when we talk about the image formation, in the case of mirrors also we have done two methods. What are the two methods? One is the ray diagram approach, and second one is by using the set of equations. There we call them as what, mirror equations. Here we will be calling them as the lens equations. So what is this ray diagram approach? We will try to draw the light rays coming from the object, and when these light rays after the refraction they are tracked, and we will see where the image is being formed by using at least minimum 2 rays from any point on the object. So we should have minimum what? 2 rays from any point on the object. Then only we will be able to track the image. And in mirror case, right, we already did this exercise, we have done it. In mirror case, what we generally do, we will keep the objects on the principal axis such that the head will be lying above the principal axis and the toe or the bottom part will be lying on the principal axis. That is how we will generally keep the objects. We will call it as what? Erect position or upright position. And we will track what is the image of the head by drawing the ray diagrams for the head of the object. We will try to locate what is the image position for the head of the object. And we will see that the bottom will be lying again the principal axis in line with the image of the head. Like if you are tracking, the image of the A is, say for example, A dash, it is happening here. Then B dash will be just in line with that, it will be on the principal axis. So this is, the sort of an easy workaround that we did in the case of the mirror ray diagram. So essentially we will be required to do only the image formation for the head of the object by using the ray diagram approach. Now here also we will try to do the similar thing, but here the standard rays that we use, like when we are drawing the ray diagrams, right, we have used a standard rays in case of mirrors. Here also we will have the standard rays. So we need to go through what are these standard rays that we are going to use in order to get the image location by using the ray diagram method. So first standard ray is, if you have a ray which is parallel to the principal axis of the lens, after refraction, right, the rays will pass through the principal focus, in which case, in case of the convex lens. That's why the convex lens, this is the focal length that we take, right, will be what? Positive. Or they appear to diverge from it in case of the concave lens. So when you have a light ray which is parallel to the principal axis, convex means what? After refraction it will go through the f2. Concave means what? After refraction it will appear to be coming from f2. Okay, so this is the difference between convex and a concave. Second standard ray is, if you pass a ray of light through the optical center, means we are passing a ray of light through the optical center, right, then we will consider that the ray will just go undeviated. The ray will simply go as it is. So here when we consider the small portion close to the optical center, right, this is almost like what? It's almost like a rectangular slab. Remember, in case of rectangular slab, when we are incidenting a light, what is going to happen? The emergent ray will be parallel to the incident ray, right? Which means what? The assumption that we make, so when we are focusing a light ray onto the optical center, it will simply go undeviated. So that is an important line that we will be using while drawing the ray diagram. And this assumption is coming from where? It's coming from the rectangular slab. When you incident a light ray on the rectangular slab, the final emergent ray will be parallel to the original incident ray. But remember, in that case what we talked about? We talked about something called as lateral shift. We talked about something called as what? Lateral shift. But here why we will neglect the lateral shift is because we are considering that the lens is having a very small aperture. The lens aperture is what? Very small, which means the rays coming and incident, they will be almost close to the principal axis. The rays will be almost close to the principal axis. Okay. Under the assumption, we can neglect the lateral shift concept. So what we'll take is, we'll take that the ray is just simply able to pass through. The third standard ray is this. If we have the light rays passing through f1 in case of the convex lens. In case of convex lens, light rays passing through f1, right? Then after refraction, they will emerge parallel. This is coming straight from the definitions, isn't it? In case of concave, what is it? If we incident light rays pointing at f1, Then after refraction, what will happen? They will emerge parallel. So this is also the definition of F1. So if you look at the standard rays, right, they are coming from where? Definition of F1, definition of F2, and third standard ray is what? If you pass a ray incidenting on that optical center, it will just go undeviated. These are the three standard rays. Now using them, we will try to look at first the convex lens, and we'll go to the concave lens. So we'll see what kind of image formation can happen through these lenses. Okay, and this ray diagram method is something that is not going to be important for the competitive examinations except for the results. Okay, so if you are somebody who likes to remember these results as it is, then it might be of help to you, at least in solving some quick and straightforward questions. So look at the convex lens. We are starting with a position where the object is beyond 2f. Always we'll keep our objects on the left side. Okay, and the assumptions we are making are that this is the thin lens, and on either side it is the same medium, which is generally air. That's why you can see the distances will be what? Identical. That is the reason why the distance will be what? Identical. Otherwise we can even name them as F1, F2, 2F1, 2F2. Instead of just calling them as F1, F1 both sides, we can call it as what? F1, this is 2F1, this is F2, this is 2F2. Okay, now look at this. The object is beyond 2f, and if you draw a ray parallel to the principal axis, after refraction it will go through the f2. If you draw a ray which is passing through the optical center, it will just go undeviated. They both are converging at this particular point. Means this is the image of the head. Let's say this is A, toe is B, means this is our A dash. Exactly in line with A dash on the principal axis, we'll have B dash. So what do you observe here? It is a real image. Why? Because it is happening because of convergence of rays. It is of course inverted and it is diminished. So when you have the object beyond 2f, the image will be what? It will be a real image, inverted and diminished. Now here I want to recall one thing. In case of mirror, right, in case of the mirror, like look at this, a concave mirror, right, this is what generally forms the real images. A concave mirror is what generally forms the real images. How it will form the real images? By the convergence. So in case of the mirrors, we will have the real images formed on the left side. In case of the mirror, we will have the real image formed on the left side. In case of lens, real images will be formed on the right side. In case of lens, right, real images where they will be formed on the right side. Okay. Now we'll come to the second position. This is exactly at 2f. If you have an object exactly at 2f, look at this. We'll draw a line parallel to the principal axis. After refraction, it will go through the focal point. We'll draw a ray passing through the optical center P. It will just go undeviated. Now because of symmetry, right, we'll see that the image will be formed exactly at 2f. Height of the image will be same as height of the object, but it will be inverted. So it will be what? A real image, inverted and same size. This is about the image characteristics when we have the object at 2f. Next we'll come to the object placed between 2f and f. So here also you can see, draw ray parallel, it will pass through the focal point on the other side. Draw ray passing through the optical center P, it will go undeviated. Where do we see? The image is formed where? It is getting formed beyond 2f on the other side. So what is this image? It's a real image because it is forming because of convergence. It is inverted, but we'll see it is what? This is A dash, this is B dash. It is magnified. So when you have the object between 2f and f, the image is what? Real, inverted and magnified. Now the extreme case of this is what? If you take the object closer and closer to the f, what is going to happen? The image is going to move farther and farther. The limiting case is what? When we bring the object almost at the F, then we will see that the refracted rays, right, they will become almost parallel. Means we can say they are going to be meeting at infinity. When they are almost parallel, we will say what? They are going to be meeting at infinity, which means the image thereby formed, right? So look at this. Wherever they meet, this length is what we are calling as the height of the image, right? So when we say they are meeting at infinity, means the size of the image is not just going to be magnified. What we have to say, it is going to be highly enlarged or magnified. But characteristics will be same. It will be a real and inverted. So this keeping the object at F is a limiting condition. Means what? Between 2F and F you are having, means image is formed beyond 2F on the other side, right? Beyond 2F on the right side. If you bring the object closer and closer to the focal point, the other side image will be going farther and farther. It will go all the way up to infinity. But the characteristics will remain the same. It will be real inverted. But in terms of magnification, what is it that we will say? It is highly enlarged. Okay. So this is about the image characteristics when we have the object at F. Now the last and the case where we have a deviation is when we have the object between F and optical center P. So if we have the object between F and P, then look at this, we are drawing a ray parallel to principal axis. After refraction, it will go through the focal point on the other side. If we draw a ray passing through the optical center, it will go just undeviated. Now when you look at these two rays, look at them, they are actually diverging. They are not going to meet, which means what? They appear to come from a point on the left side. So this image here is what? It's a virtual image. What is this image? It's a virtual image. In case of lenses, remember, real images will be formed on the right side, virtual images will be formed on the left side. Okay, so it's a virtual and erect. All the images that we have seen so far, right, are what? Inverted, real inverted, but here it is what? Virtual erect, and of course this is magnified. So what is the characteristics of the image formed? It will be virtual erect and magnified. So if we have the question like convex lens, in which position it will be able to form a virtual image? When it will be able to form a virtual image? When we have the object kept between F and the optical center. It will give us what? Virtual erect and enlarged or magnified. Okay, so this is the what we can say abnormality with regard to the convex lens that we need to remember. Okay, now in case of mirrors, right, just to show the difference, in case of the mirrors, for a concave mirror we have talked about different scenarios, but for a convex mirror, right, we have only one case. Other than the object at infinity, we have only one case, correct? In the case of the lenses, right, we have discussed for a convex lens different scenarios so far. For a concave lens, we will have only one case other than infinity. It is the reverse. Focal length wise, see, this is how we will have to remember these things so that we will be able to recall them quickly. Focal length wise, same. Convex, both cases positive. Concave, both cases negative. In terms of the number of possibilities of the image formation, right, mirrors, what is it? Concave mirror, we talked about multiple scenarios. Convex mirror, only one. Other than infinity, only one case. When it comes to the lenses, right, it is the reverse. Convex lens, we have talked about multiple scenarios. Concave lens, we'll have only one case other than infinity. Okay, so look at the concave lens. We'll talk about the infinity later, but look at, if we are keeping the object anywhere, on the principal axis. Object will be kept on the left side, right? The object will be kept on the left side. Okay, wherever we keep the object, we will be forming the image between the optical center and F2. So where the image will be formed between the optical center and F2. Now the image is formed on the left side, right? So left side means what is it? It's a virtual image. So it will be a virtual, erect and diminished. So look at this. We have kept the object somewhere. We will draw a ray parallel. After refraction, it will go such that it will appear to come from the F2. We will draw a ray passing through the optical center. Now both these rays, let us call them as 1 and 2. They are basically diverging. They appear to diverge from a point here. So if this is AB, this point here is what? Our A dash. Just below that we will have the B dash. So we will see what is the image. It's a diminished image. It's a virtual, erect and diminished image, where the image is going to be formed between the optical center and the F2. So this is the image formation because of a concave lens. Now what is the extreme case of this? If you have the object itself at infinity, right, we will have the light rays coming almost parallel. After refraction, they will emerge like this. They will emerge as if they are coming from point F. So this is in fact the definition of our focal point, right? So where the image is going to be formed at the focal point, at the focus. The nature of the image will remain the same. Look at this. Nature of the image is what? Virtual, erect. But it will now be not only diminished by small amount, it will be what? A point size image. Means we will say it is what? A highly diminished. So what is it? It's a highly diminished. Okay. So the nature will remain the same. Virtual, erect will remain the same. But in terms of the magnification, right, generally a concave lens diminished. But in this case it will be what? Highly diminished, or we can say point size. So this is about the image formation from convex lens and concave lens, what we study by using the ray diagram approach. Now if you are able to remember these things, as I said, this will help us to solve any quick questions. Like sometimes they might even give some throwaway questions based on the reasoning. Like, you know, they will say lens is giving an image with these characteristics. What is the type of a lens? Like that we can have sometimes questions being given. So if you are able to remember these image formation characteristics, means we will be able to answer those kind of questions. Okay. Now let us look at the equation approach. So equation approach is in case of the mirrors, we have the mirror equation. What is the mirror equation? 1 by V plus 1 by U is equal to 1 by F. In this we are going with the usual notation. V means what? Image distance. U means what? Object distance. F is the focal length. So we'll get a plus. In case of the lens, right, this is the lens equation. What is this? Is the lens equation. 1 by V minus 1 by U is equal to 1 by F. In case of lens, what is the relation? 1 by V minus 1 by U is equal to 1 by F. Okay. And for an image, right, one thing is to know where the image is formed. Other thing is to know what is the magnification. So in case of the mirror, we have used the linear magnification. Here also we use linear magnification. So what is the linear magnification definition? We will define it as what? The height of the image by height of the object. Same thing. So the image height by object height. Remember, in case of the mirror, what is it? Minus V by U. So here it will not be minus V by U, just it will be what? V by U. Now we'll have a question as to how do we remember this without getting confused. So this is how, you know, I will probably suggest you can try and remember. Maybe you can have other alternative methods of, you know, easily remembering it. Okay. So look at this. I'll say triple M. So triple M means first is, you know, mirror, second is magnification, third is minus. What is this triple M basically represents? I mean, this is a kind of a mnemonic that you can use to remember. What is it? Triple M means what? Mirrored magnification minus. So in the magnification formula for the mirror, right, we'll get minus. And when we get a minus in the magnification formula, the equation, we will not have a minus. That's how we remember. When we get a minus in the magnification formula, equation will not have a minus. The exactly reverse will be in case of the lenses. Look at this. Mirror magnification is minus, right? Lens magnification plus. You get a plus here means in the equation we will get a minus. It will be what? 1 by V minus 1 by U is equal to 1 by F. Okay, so that's how you can probably try and remember it. Maybe if you are able to find a better way to remember, you can do that also. Okay, but the only thing is we should make sure that we don't mess up with this. So for lens equation, we should not just go and put the mirror equation. That we should avoid. So what is it? In case of the mirror magnification, we'll get minus. Magnification minus means actual mirror equation plus will come. Exact reverse will be for the lenses. Maybe that way also you can remember. Okay, so this is about the lens equation and the linear magnification caused by the lens. Now with these equations, right, what we will be able to do, if we know the object position and the focal length of the lens, we will be able to find out where the image is getting formed, and also we can find from the magnification, right? Remember already we talked about how do we analyze things from the magnification. Magnification positive means what? The image will be erect. Magnification value less than 1 means diminished, more than 1 means enlarged. Like using the magnification value, right, we have seen already in the case of mirrors what kind of information we will be able to know about the image formation, correct? So here also magnification factor will be useful for us. It will tell us the characteristics of the image, like whether the image is erect or inverted, or whether the image is diminished or enlarged. This we will be able to know by using the magnification factor. Okay, and from the V value, V will give us what? The position of the image, right? If the image is getting formed on the right side means what? It will be a real image. Remember lenses. Lenses means what? If you have a lens, right side, we will have the real images. Left side, what we will have? We will have the virtual images. So from the value of this V and M, we will be able to conclude the characteristics of the image formation because of the lenses. Okay, and in case of mirror, we talked about the converging or diverging ability of a mirror by using the power. Here also for the lenses, right, the converging ability or diverging ability of a lens is quantified by using the power. So power will be measured as the reciprocal of the focal length. Why? If you have a lens which is able to converge the parallel rays to a very small distance, focal length in this case is what? Small, which means the converging power of the lens is what? Higher, isn't it? The converging power of the lens is what? High, which means what? We'll have to define the power of the lens just like the way we define the power of the mirror, right? Here also we'll define it like what? Reciprocal of the focal length. If the focal length is in meter, then the power will be coming in terms of what? Diopter. So which is what? Like meter inverse. Okay, now for a converging lens, already we talked about it. For a converging lens, focal length is what? Positive. It means power also will be positive. Since focal length is positive, power will be what? Positive. For a diverging lens, focal length will be what? Negative. So power also will be negative, because here there is no modulus or anything. It is just simply 1 by F. Okay, we'll discuss a little bit more about the power, and we'll have some application level questions based on the power also. Like if you have combination of lenses, how do you find the power of the combination of lenses? Like that we'll study about it. Okay, but this is about the set of equations that we are going to use to understand the image formation by the lens. In the next class, what we'll do is we'll start with some basic level questions on how do we use these equations to understand the characteristics of the image form, and also once we cover the basic level questions, we'll try and look at some more detailed application level questions on these equations. Okay, so we'll see you in the next class.